Good morning, good afternoon, all. Thank you very much for joining this session. I mean, just to make sure that for those who have joined just now, just to make sure you're on the right talk track, this talk is on the importance of distributed SQL in the age of cloud native apps. I'm Srini. I'm a solutions engineer with Yugabyte. What is Yugabyte? Yugabyte DB is a distributed SQL. Which is essentially cloud native with all the cloud native characteristics like it's highly available and resilient, horizontally scalable and vertically scalable, geo-distributed. It's a strongly consistent database, open source database, which is cloud native, right? So we have a lot of cloud native characteristics in this frame. I'll try to uncover as much as I can as we move on. The obvious question is, what is the role of cloud native distributed SQL in the age of cloud native apps, right? The application architecture is changing, evolving a lot. Why not we can't address the changing demands of our application architecture with the existing relational single node database system or any of the different flavors of NoSQL, right? The obvious question to understand is before getting into what is Yugabyte, what role does it play, what is distributed SQL and all. First, try to understand why distributed SQL, right? If you don't understand the need for a distributed SQL, there is no point in going through what is distributed SQL and other things, right? The complexity space is something that we need to understand. What is the need for a distributed SQL in the changing demands of application architecture, business demands, growing user base, and so on and so forth, right? What you're looking at is a traditional monolithic based architecture, right? So everyone, I assume that everyone is familiar with this architecture. A lot of applications in productions are built off of this architecture, right? Essentially, you'll have different tiers in your application, often tightly coupled, bundled together, would be talking to a single node RDBMS system. And then depending on your application's SLAs requirements, if it's a category 1 application with high availability requirements and so on and so forth, and you would find a standby instance that will be either asynchronously or semi-synchronously replicating data from a single node RDBMS system. So this application architecture has served us well. Even you would get to see this application architecture in production in a lot of enterprise space today. It's serving us well as long as the load is predictable, the business demands are not rapidly changing, and the user base is constant, right? And from an operations standpoint, if it's for critical, B2C based apps or B2B based apps, it's extremely complex to manage because essentially database is a single node system. Whenever you need to patch that machine, or whenever you need to upgrade that instance from one version to another version, it often incurs downtime, right? And it adds more complexity to the application layer. So you have to build some logic in your application layer to minimize the downtime as much as possible. So it's something would be appreciated by the ops folks, providing the changes that are happening in the application space, right? So that's what we have started to see from a modernization standpoint. The application architecture, whatever we have had in the past in terms of monolithic, is not scaling well, right? It's not meeting the business demands, and as well as it's not meeting the exponentially growing user base, right? That's when we started to see this transformation happening on the infrastructure space as well as on the application space, right? The advent of cloud brought in infrastructure as code, on-demand provisioning of various infrastructure resources like virtual machines, storage, within few minutes. And that has paved the way to the natural progression in the application layer transformation, which is build once, run anywhere, container paradigm, complemented with cloud agnostic Kubernetes orchestration as induced a lot of transformation in the application layer, right? And obviously, we started to see a lot of patterns emerging, like API-driven containers, monolithics to microservices, not just limited to the technology side of things, but also attributed to people and process, like the silo devs and ops have started to collaborate more, work together more, where they were building the services that they were responsible for operating in production as well. And on the process side, we started to see things like continuous integration, continuous deployment, and so on and so forth, right? And obviously, the architecture has evolved. And just to meet the growing demands, a single tightly coupled application is now being broken down into multiple domain-driven services that can be autonomously and independently built and managed in production, right, by different set of teams. But the data complexity still remains the same, and the non-functional requirements from a data layer standpoint, it still remains the same, right? So all these services need scalability, and operations need to be as simplified as possible. And none of these services can afford to have downtime, right? And then the level of complexity, whatever we have had with a single node system, it's kind of extrapolated now, right? So every service in this whole, every broken down microservices in this entire application demands the same level of high availability and scalability requirement. And obviously, these different microservices have led to different discrete data patterns, data requirements per se. Some of the services are read-heavy services. We started to see things like CQRS, where the writes were routed to a separate instance and reads were often served from different set of instances. And if the user base is geographically distributed across, then we started to see a lot of instances, a lot of application instances serving locally. But the data is still confined to a single instance that's running on a remote mission that attributes a lot of latency per se. The read patterns are different, write patterns are different, and then these services have start to demand discrete data-oriented requirements like notify different services in the entire system to be informed whenever there is an update, or automatically purging older data sets and so on and so forth. So obviously, the single node database system, RDBMS system, can be used to address all these demands, but a lot of heavy lifting needs to be done on the application layer, right? So a single node system is not going to be sufficient. So we have to run multiple instances of this database. The application layer has to build all those complex logic into it. It has to decide which instance of the database to talk to. And also from an operational standpoint, each database needs to be replicated from a high availability standpoint, so that DR, backup, and so on and so forth. It has increased a lot of complexity, right, from a data standpoint. So obviously, the data layer needs to be transformed. This is what we are seeing right now. Which is the data layer is the one that's sitting in between our infrastructure and the application layer, which are both kind of cloud native, right? So the infra is something that you can that you can provision on demand thanks to all the automation software out there, the likes of Terraform, Ansible, and other things. The application layer is also cloud native, the likes of Kubernetes. Promises your application to be able to run on various clouds, and you'd be able to seamlessly scale your services on demand, right? So the data is the odd man out, which needs to be obviously transformed to cope up with the changing demands of these two layers in between, right? So that's when we start to see trends like NoSQLs emerging. The NoSQLs seem to address all the scalability requirements from a single node RDBMS system, right? The NoSQLs are essentially distributed, so the architecture resiliency is built into it, and it's horizontally scalable, so that you'd be able to scale your NoSQLs in line to your application architecture scaling. And based on how your deployment patterns are spread or distributed across, you'd be able to distribute your data across as well. It seemed to address some of the shortcomings of your traditional RDBMS systems. But at the same time, NoSQLs gave up on two of the core features of RDBMS, which is like NoSQLs are not fundamentally ACID compliant. So some of the flavors of NoSQLs have started to support ACID, but not in a quote unquote ACID fashion per se. And NoSQLs don't support SQL APIs per se. A lot of applications, frameworks, tool sets were built around SQLs. SQLs were very powerful, right? So when it comes to NoSQLs, then you have to learn different set of APIs and dialects to deal with, right? Just to visualize the level of complexity that we see in the enterprise space, right? What you're looking at is a sample retail e-commerce application. It was a single monolithic based application, hardly, being served off of a single node database system. Now it's being broken down into multiple services, right? Each service demands its own flavor of database. Some of the services require a traditional RDBMS system. Some of the services would require different flavors of NoSQLs based on how the SLAs are defined for the services, right? Scalability is essential or high availability is paramount for the services, then those services would prefer to use different flavors of NoSQLs, right? The complexity has grown a lot, not only the application level complexity. From an application standpoint, we are trying to consolidate the platform layer with a single runtime per se, where Kubernetes is becoming the sort of global control plane to deploy applications across. Whereas from a database standpoint, which is extremely complex, we start to see a different flavors of it, right? If you try to understand the complexity that devs and ops in different personas of the organization have to go through in order to manage these different discrete services, is immense, right? Developers have to learn two different set of APIs. If it's SQL, then they would know SQL-based APIs. If it's NoSQL, they have to unlearn and learn NoSQL specific APIs and the way how you interact with NoSQL services, right? And essentially, a lot of frameworks and tools were built based off of SQL APIs. If it's going to be NoSQL, then again, you have to go through the learning phase of learning learning the nuances of those APIs, or you might end up building your own API based on it if you don't find or compatible or supported APIs based on it, right? And ops team also have the same set of challenges. I mean, a single node system itself is complex to manage at scale across different applications when it comes to data. Now we have a myriad of databases in the enterprises, right? Combination of SQLs, NoSQLs, and so on and so forth. The runbooks, the playbooks are essentially different. The way that you manage, build, manage, and operate it at scale across various applications, fulfilling all the demands of SLAs is really, really challenging, right? But what we need from a data layer standpoint is essentially this, right? So a database is expected to fulfill all these characteristics, right? So the architecture needs to be resilient because in the world of cloud native commodity hardware, anything can fail at any point of time. The database should survive, right? And it should be horizontally scalable. It should be, we should be able to linearly scale it along with the elasticity provided by the underlying infrastructure, as well as the horizontal scalability being demanded by the applications that are running on top of it. And you should be able to seamlessly distribute and keep it as close as possible to your application layer so that you'd be able to serve your users closely where they are based off of, right? So, and at the same time, ACID is paramount because that's one of the core selling points of the traditional RDBMS systems, right? So it needs to be ACID compliant, and SQL API is also essential. It's important because a lot of frameworks are built around it, and a lot of applications still allow the SQL APIs, right? Essentially, from a database architecture standpoint, we want the architecture to be evolved this way, right? Not only the infrastructure and the application layer, we want the data layer to be cloud native, right? To be able to seamlessly deploy it across different form factors, be it VMs or Kubernetes, or be it on public clouds or in private data centers. We want the data to grow, data services to grow, sit and be aligned with the application and the infrastructure architecture, right? And this is what we expect out of the database, right? So the services are growing rapidly to meet the growing business demands, exponentially growing user base, and so on and so forth. We want the data to closely follow our application architecture. If the apps are geographically distributed across to serve, to meet where the users are, we want the data to closely follow the apps as well. That's where distributed SQL comes in, right? So distributed SQL brings the best of both the worlds, right? The SQL API compatibility plus ACID transactions from a traditional RDBMS system, plus the distributed nature of a storage being provided by NoSQLs. Distributed SQL brings in both the things. Sometimes you would have heard people calling it as new SQLs. Essentially, distributed SQLs and new SQLs are more or less the same. Basically, it gives you the best of both the flavors of database services, right? Yugabyte DB is one such flavor of distributed SQL, which brings the best of both a traditional RDBMS system plus the scalability and resiliency features being offered by a NoSQL from a storage standpoint. What you're looking at is the high-level logical architecture of Yugabyte DB. It's self-explanatory from this architecture, right? The database needs to be cloud native, meaning that needs to be cloud agnostic, right? We don't want to build our database systems tightly coupled to kind of engineered hardware per se. If that's been the case, and it's not going to be portable, may not be able to get the benefits out of the kind of services that you get out of the cloud, right? So essentially, Yugabyte DB is built from ground up to be cloud native. You would be able to deploy it across various form factors like containers, VMs, public clouds, on-premise data centers, and so on and so forth. And at the top, the query layer is pluggable, which is, it needs to be SQL compliant, right? So we don't want to have our developers to learn new set of APIs to use the database system. We want to simplify the developer experience. We want our developers to get started as soon as possible, right? The APIs that they are used to, they are familiar with for the past 20 plus years or so. We want them to continue to use the same set of APIs. So the API layer is pluggable, essentially to address discrete set of use cases, right? It supports two different APIs, SQL, Yugabyte Structured Query Language, which is built based off of Postgres API. That is meant for traditional RDBMS-based workloads, all of your system of records, engagements, those kinds of use cases, workloads. You can use YSQL. And YSQL is another query layer. It's again another API being supported by Yugabyte, which is Yugabyte Cassandra Cloud Query Language that has its roots in Cassandra API, right? This is meant for high write throughput, massive write intensive kinds of workloads like IoTs, stock tickers, and similar to those, right? The reason to have these two APIs is to address different set of use cases. We don't want to bombard the enterprises with different flavors of database per se, right? So have a single database system which would essentially address most of your discrete use cases, right? And the middle tier is the important one, which brings out all the cloud native characteristics from a database standpoint. It is built from ground up to be distributed, scalable. The data gets sharded and replicated seamlessly across, and it's all being built within the software layer itself. And it's 100%, and it supports ACID transaction, and it's SQL compliant as well, right? Under the hood, as you can guess, like any distributed system, it comprises of two important processes. One is the master service, which is responsible for managing all the administrative related tasks, keeping hold of all your metadata information, making sure that the metadata is distributed across whenever the data needs to be re-replicated, initiate that background process, and then taking backup and restore of your system, and so on and so forth. All those sorts of administrative activities are being taken care by the master service. And T-Service service is T-Service service is the one that's responsible for managing your data. As you can see from the slide, the clients, the consumers of the database would often interact with the T-Service service. That's where the data resides, right? And it provides all the cloud native characteristics that I mentioned about. So data gets any table that you create within the system, it gets sliced into multiple shards, and these shards are distributed across. And based on the replication factor, you would find multiple copies of the same data just to ensure the resiliency is being taken care of, right? So in the world of distributed computing, that on a commodity hardware, the networks are often not reliable. Often we assume that it's always reliable, but that's not the case, right? So any system can go down. Any network partition could happen at any point of time. We would still want the system to be functional, operational, to be able to continue to serve and read and write traffic, right? So those are the characteristics that's been built into it, right? We'll go through all those characteristics on a high level, right? Again, the deployment pattern is essential because it's cloud native. We don't want the database to be tightly coupled to a specific cloud or hardware per se. And we want the database to be that it should be flexible from a deployment standpoint, depending on the requirement or the nature of the applications that you build, right? If it's a category 1 application where you want to have zone level resiliency, then single region multi-zone is where you create your cluster across multiple zones. Or if you want to have region level failure, then you'd be able to create a cluster across multiple regions. And then if you want to have cloud level resiliency, you'd be able to create a cluster across different clouds as well, right? So, I mean, in the sense, the representation is more from a public cloud standpoint, but doesn't mean that it's limited to public cloud, right? You would have the equivalent of it in your private data centers as well. So the zone could be your fault domain in the form of racks with dedicated networks, cooling systems attached to it, and so on and so forth, right? So the same thing can be related to both public cloud as well as on-prem as well. Let's look at the cloud native characteristics real quick, right? So I said that the database system needs to be SQL compliant so that developers can get started real quick. We don't want to have our developers to learn another new technology per se. Essentially, I mean, you would be able to easily relate your application architecture as well, right? So when it comes to Kubernetes, we have started building stateless applications to have that horizontal scalability, right? From a Yugabyte standpoint, that's what we do. From a query layer standpoint, we run stateless Postgres process in every node in the cluster. So that's a comparison between a single node Postgres system and what you see with Yugabyte as well. Let me quickly get the pointer just one second. So in the case of single node system, in the case of Postgres, it's a single node, the query layer and the storage layer, both of these run in a single machine. Whereas in the case of Yugabyte, it's distributed. You'll find a stateless process of Postgres living in every node, which would be working with the distributed storage layer. That's how it's segregated to provide that horizontal scalability from a query layer perspective, so that whenever the users or clients would interact with, every node in the cluster could serve read and write traffic. At the same time, the data is distributed at the storage level, just to ensure that the resiliency aspects are taken care of, right? It's SQL compliant distributed storage. It supports both consistent as well, synchronous as well as asynchronous replication within a cluster. It's strongly consistent. So from a CAP theorem standpoint, Yugabyte DB favors consistency whenever there is a network partition. That's the reason we have to ensure that the data replication within a cluster is consistent and it's synchronous. It's happening in a synchronous fashion. Whereas across clusters, when you want to run active of deployments, depending on your requirements, then we will be able to facilitate those kinds of patterns over asynchronous replication as well. So as I said before, Yugabyte DB supports distributed query processing. Since we run stateless Postgres in every node in the cluster, every node can do your read and write traffic, and it supports distributed consistent ACID transactions as well. And what we have built on top of YSQL, it has its roots in Cassandra, so it supports all the capabilities of Cassandra plus few other things in the forms of strong, consistent secondary indexes, native JSON support, and similar features as well. I said that it's strongly consistent because this is essential. In the case of a single node system, it's a single point of failure, right? So that's when you have to run a standby instance. You need to have another replica. If the primary instance goes down, then there will be a downtime to promote your follower to be the leader and so on and so forth, right? And it is operationally demanding as well and complex. So in case if you don't follow your playbook in the right manner, so you end up doing a lot of mistakes, right? So whereas in the case of Yugabyte, it has a strong data replication. So depending on the replication factor, which you define at the cluster level, you'll find multiple copies of the same data. So in this case, the replication factor is 3. So every shard in the database would have 3 copies. So that if one copy, or depending on the level of resiliency that you need, if some of the copies go down, you still have the clusters intact. You'll find the surviving copies in other nodes in the cluster that would continue to serve your read and write traffic, right? So this is within a cluster. And other thing is, so again, it has to support the evolving application patterns, right? So often we see the user base is geographically distributed, and we get to see applications being distributed across the globes. We see patterns like multi-cloud, hybrid cloud, where you have the instances of applications being deployed across. And we want the data to closely follow our application, right? So wherever the app goes, the data follows. That's the pattern that we want to see, right? So it supports read replicas as well. Read replicas are nothing but the extended arm of your primary cluster. The role of your primary cluster is to serve read and write traffic. And if you have user bases that are distributed across where you want to spread out your read traffic, then you can create read replica clusters extended to your primary clusters, right? And the replication factor in this read replica can be different as well. So you can have 5 RF read replicas being spread across different clouds, different regions in the APAC region, right? So what you're looking at is the primary cluster is based out of Americas, and then you have read replica clusters in Asia and Australia serving your application requirements across the globe, right? And then it also supports active resilient topology. Unlike a traditional system where you run a primary instance and a standby instance, in the case of Yugabyte, you can have 2 clusters running in active mode. And at the same time, it supports both unidirectional and bidirectional, right? So all your DR related challenges are completely addressed through this requirement, right? You don't, I mean, in the case of especially in the financial industry, every 6 months, enterprises have to go through the DR tool, right? So all those things can be addressed with this pattern, right? So you can have your primary cluster deployed in your primary data center, and then another active primary cluster in your DR data center that can serve both your read and write traffic. And then you can enable replication between these 2 clusters as well. So this is active topology, and you can apply the same read replica feature to this topology as well. So I can have my active if majority of the user, if the user base is based out of let's say 70% or 80% of the user base is based out of Americas and Europes, then you can have your primary clusters deployed there. And to serve the remaining user base spread across the rest of the world, you can have you can extend your primary clusters with read replicas being deployed in other regions across the globe as well. And geo-partitioning is also one of the features of a distributed SQL. So this is vital from a GDPR-based requirements, right? So though cluster can be stretched or distributed across different globes, we still want to have the data to be pinned to a specific region per se, right? So if the users are based out of US, and if the regulatory requirements are defined in such a way that the data can't leave the US region, then you should have capabilities in the database to pin the data originating the US to the US server itself, right? And the same thing is applicable for Europe, Asia, and rest of the world as well. So the geo-partitioning, the pinning your data based on where it originates to a specific region is part of Yugabyte database itself, right? And on the application side of things, it's not just the database alone, right? Because it's a distributed database, you'll have multiple nodes in a cluster. And you need to have some level of smartness to be built into the client layer, right? So if you don't have the smartness built in, then client would still do a kind of heavy lifting, right? Because in order to talk to a distributed cluster, first of all, client should know the whereabouts of all the instances. So if one node is not reachable, then the client should be smart enough to move to the next node in the cluster to route the request, right? So it's a kind of heavy lifting that the client has to do. And then the discovery is something that's also complex, because in a distributed system, as you can imagine, nodes can come and go at any given point of time. Then the client should be smart enough to understand the cluster topology all the time, right? So how many nodes in the cluster are there? What is the health of the nodes? Can I send my read and write traffic to those nodes or not, right? And topology awareness is also very important, because from a geo-partitioning standpoint, if the user base is originating in the Americas, and if you want the request to be serviced within America itself, then your client should know which nodes in the cluster to talk to, which are the nodes that are running in the America data center, right? So building all those capabilities as part of your application is not an easy thing to do, right? So that itself is a complex product per se. So in order to minimize that, what we have done is we have built a client library, which is again wire compatible with Postgres. The Yugabyte smart driver is built based on Postgres driver, which is cluster aware and topology aware, right? Meaning that it auto discovers all the nodes in your cluster. As the nodes, as you keep scaling your clusters out or scaling down your clusters, based on how the cluster topology changes, the driver detects, discovers all those changes automatically. And it's topology aware as well. So if a cluster is stretched across 2 different regions, it exactly knows how many nodes per region and how these nodes are tagged to, right? So if you have a cluster created between Europe and Asia, and you know exactly the number of nodes in Europe, number of nodes in Asia, and depending on where the client requests are originating, it will be able to pin the request or route the request to the appropriate regions, right? So again, from a client standpoint, they just have to express that as part of the driver initialization. If the request needs to be always routed to the nodes in the European region, then client would set that property, and based on that, the driver would automatically bring in the nodes that are part of European data center, right? So that capability is built into it, and obviously it's not just limited to just from a driver standpoint. We want that to be seamlessly integrated with other popular frameworks as well, right? So from a Java standpoint, Spring is very popular, and similar to it, we start to see other frameworks like Quarkus, Micronaut as well. And these capabilities are natively built, whatever the smart driver that I mentioned about, it's seamlessly built into the Spring framework. So we have our abstraction based on Spring Data, our own implementation based on Spring Data abstraction, that's Spring Data Yugabyte, that provides all those capabilities out of the box, right? So from a consumer standpoint, you don't need to learn anything new. It's still your familiar driver. However, whatever the way that you have connected to Postgres using Postgres driver, you continue to follow the same norms. Just the declaration step would be different. Instead of JDBC Postgres, it would be JDBC Yugabyte, something like that, right? And from a consumption standpoint, the ecosystems, whatever that were built around all these traditional RDBMS systems, right? You can continue to use all those things, right? So whatever the frameworks, tool sets that were built to work with Postgres, you can continue to use all those things with Yugabyte as well, because it's Postgres API compatible, right? So that's on the application awareness part, right? It's time to have a sneak peek of the product that we have built in and the capabilities, whatever that we have built as part of this database product, right? So from a transformation standpoint, this is something that we start to see everywhere, right? So if you look at the cloud services or the services that we built in every enterprise today, so platform as a service, infrastructure as a service, and database as a service sort of capability that we want to build everywhere, right? It's not just only in public clouds per se through the likes of managed services, but at the same time, if you have a self-managed team, then you want to build these capabilities anywhere that you would go, right? So whereas it's multi-cloud or hybrid cloud or within your private data center, you want to have these capabilities to be built in. And it's not an easy thing to build from ground up, right? So the challenges are always like with different RDBMS systems or different flavors of RDBMS and NoSQL, the upgrade is always ceremonial. That incurs downtime. It has always implications on the application side. And these databases are continuing to receive multiple releases, patch releases, and so on and so forth. So it's going to be a never-ending process per se, right? So the ops are often bombarded with all these different requests. One team would say that I want to run latest version of my database. Other team would say that I want to run a stable version of the database. So often you have to maintain multiple versions of the database. At the same time, you need to make sure that these different releases are patched enough so that it's free of vulnerabilities, security-related issues, and other things as well. And we want to bring in the best developer experience as well. So the database should be, they should be able to consume these services on demand through APIs, like the way how they consume to a Kubernetes as a service, right? And we want to bring in a similar kind of capabilities to the database service as well. And essentially, when you look at it from these different personas, right, from a developer standpoint, you want to get started as quickly as possible. SQL compatibility is important. All the frameworks, tool sets, whatever that they have used to, that's important. And they want to consume these data services across different application architectures, whether it's built based out of containers or traditional monolithic data. They should still be able to consume these data services. From an ops standpoint or cloud ops standpoint, all the data related challenges need to be completely addressed, right? So seamlessly, they should be able to create multi-tenanted, different size clusters, and be it upgrades or patches or rollouts, product upgrades or whatever it is, it has to happen seamlessly, right? So nobody can afford to have downtime per se, right? So if it's a critical business facing application, and I mean, in the sense, if it incurs a significant, even if it's a 5 minutes downtime, it's going to be a sensational news the next minute itself, right? So the social media is going to bombard it with all these kinds of negative feedbacks about the application, right? So nobody can afford to have such kind of negative image when it comes to B2C or critical business applications person, right? So these are all the asks that we essentially look at from a database product, right? It's not just about creating the product or providing all those capabilities, but make sure that we address all the key asks of different personas in the organization, right? Let me do a quick demo now. All right. What you're looking at is I spoke about the key asks of different personas in the organization, right? So what we have built is basically it's a piece of software. It's a self-managed Yugabyte DB software that we have built. That is something that can run it anywhere, right? You can run this software in your own data center, or you can run your software in any of the public clouds in different form factors, right? So you'll be able to run it in VM form factor, or if Kubernetes is the preferred platform of your choice, then you can run this software on Kubernetes as well, right? The first thing that we need to do from this software standpoint is, this is something that you will be able to relate to, right? So if you are building your own private data center, or if you are creating your own account in any of the public clouds, the first step is to carve out your own space, right? You'll create a VPC and then you define your segments. And once that happens, then you go and provision the various cloud services, right? From a Yugabyte standpoint, the first thing that we need to do is to bind this platform to all these different cloud providers, right? So if your requirement is to create database clusters on AWS or manage Kubernetes service in the form of EKS or AKS or in your own private data center, then you have to bind the cloud provider configuration to the appropriate you have to bind the software to the appropriate cloud provider configuration, right? So what you see in this case is I have already configured AWS. So the platform is already bound to the underlying cloud provider per se. So add configuration is more about letting the platform know how to connect to the underlying cloud provider, right? So what are the keys to connect to, and how you want your services to be provisioned, whether you want to provision it in an existing VPC or you want to create a new VPC, and so on and so forth, right? So that's the first step. So once that part is done, so these are all the certified cloud providers. So this is again, I just want to reiterate, this is a software that you can run it anywhere, and you can have this software running in your private data center, and you can create your Yugabyte DB clusters on these different clouds, right? So once you provide the cloud provider configuration for AWS and GCP, via this single interface, you'd be able to create clusters in AWS and GCP, right? So you don't need to connect to AWS console or GCP console to create Yugabyte clusters. Rather, you do everything from this single stop portal, right? Essentially, it's a single-stop self-managed portal to manage a fleet of Yugabyte clusters. That gives you the complete 360-degree view about all of your running clusters, right? And once the cloud provider configuration is done, next step is more about it's a guided flow. You have to key in a bunch of information. So it's just a name that you give, and then you select your appropriate cloud provider. In this case, it's AWS. And then once the cloud provider is chosen, you would be, these are all the regions that AWS operates on. So it populates all the supported regions of AWS, and then you can select your own region. And once the region is chosen, it populates the availability zones in that region. AP Southeast 1A, 1B, 1C for Asia, Singapore. So in this case, it's a single cluster with a replication factor of 3. That ensures that you always have 3 copies of the data, and it's been distributed across 3 different availability zones, right? So this ensures zone level failure. If 1C goes down for some reason, still your cluster will be intact to serve your read and write traffic, right? And let's say that if I want to create a multi-region cluster, then you can select multiple regions, Singapore and Bombay. Appropriately, you'll see availability zones from those 2 regions, right? So this is a single cluster deployed across 2 regions so that it can survive region level failure. And then it's next step is to choose your instance type. What should be the instance type? Choose your VM blueprint and the storage requirement. And then answer a bunch of questions like whether it needs to be exposed to the outside world or you want to create it in your private segment, and so on and so forth, and select the database version. Once you hit the create button, this is going to create the database for you, right? The creation itself is like a guided flow that you, once you answer these questions, the creation is going to happen immediately. It's just a kind of push button thing that you have to do in order to provision create clusters on demand, right? And this user interface has got, I mean, if you want to create read replica along with your primary cluster, then you can define the number of read replicas as well. And these read replicas can be on different regions, right? So my primary cluster could be in Bombay and Singapore, read replicas could be in Frankfurt. And that's how you distribute your cluster across the globe, right? And then you can select the own replication factor for read replicas and so on and so forth. So once you hit the create button, this is going to automatically, the software is going to talk to the underlying cloud providers APIs to provision all those resources, right? Things like VM storage and all those things would be provisioned automatically, right? And then just to quickly summarize from a day 2 standpoint, this is a single stop portal. This gives you the complete 360-degree view of your application, of your database cluster. And it gives you table level information, node level information, metrics being broken down at different layers, APIs, nodes, storage, and so on and so forth. And then you can initiate backup and restore from this cluster. And then if you want to do scale your cluster actions, edit universe would allow you to increase the number of nodes, or you can vertically scale, increase it from 2 core to 96 core, and so on and so forth. And you'd be able to use the same interface to upgrade your platform from one version to another version. And the upgrade usually happens in a rolling fashion. So without, just to make sure that we don't disrupt your running applications, the upgrade happens without any disruption to your applications, right? So the platform would continue to serve your read and write traffic, right? So that's pretty much on the demo. So that's what I wanted to cover today. So as I said before, Yugabyte DB is essentially cloud native with all these characteristics to make sure that the developer experience is paramount to us. So that's the reason, I mean, in the sense, the database is built based on Postgres API, and at the same time, it provides all the storage level resiliency as well. That's pretty much from my side. If you have any questions or would like to know more about Yugabyte DB, please feel free to join our vibrant Slack community. Thank you very much for tuning in.